Modern agentic frameworks like OpenClaw operate outside the traditional software sandbox. By design, they interface directly with local file systems, execute shell commands, and interact with external APIs to accomplish complex tasks. Because these agents possess true OS-level privileges, a single model hallucination or a well-crafted prompt injection bypasses standard guardrails, allowing raw, catastrophic commands to execute directly on the host machine. This creates a structural conflict. The system is asked to execute complex, open-ended user instructions while simultaneously policing its own behavior, forcing a continuous trade-off between task utility and safety compliance. Relying on an agent's internal logic for security splits its computational focus, degrading operational efficiency. More critically, it leaves the safety protocols themselves exposed to the exact same adversarial inputs the agent is attempting to process. Securing a high-privilege AI requires an architecture that explicitly separates execution from oversight. That is the exact purpose of the ClawKeeper framework. This diagram outlines the ClawKeeper methodology, deploying a defense-in-depth architecture across 3 operational layers: skill-based, plugin-based, and watcher-based protection. At the instruction layer, skills enforce boundaries. At runtime, plugins establish configuration rules, and an independent watcher provides continuous behavioral verification. In an ecosystem where threats range from malicious prompt injections to supply chain backdoors, a single-point defense leaves the system exposed. True security requires these 3 layers operating simultaneously across the entire execution lifecycle. We start at the instruction layer. This section illustrates the structured markdown policies used in skill-based protection. These policies inject explicit system-specific and software-specific constraints directly into the agent's context window. These policy documents establish immediate operational perimeters. Look at the interface here. When presented with an obfuscated base64 string targeting the host OS, the agent successfully decodes the payload, identifies the code injection attempt, and explicitly refuses to execute it, triggering the security alert. The agent reads them alongside the user prompt, dynamically aligning its actions with approved security protocols before generating a response. However, this layer contains a structural flaw. Because the security rules reside inside the manipulable context window, a sophisticated adversarial prompt can simply command the agent to ignore or delete its own safety skills. Contextual alignment gives the agent necessary agility, but placing the defense mechanism in the same channel as the attack vector makes it fragile against targeted manipulation. To protect the rules themselves, we move below the context window to Layer 2. This schematic maps plugin-based protection, an internal runtime enforcer that verifies the cryptographic hashes of critical system files like OpenClaw.json and agents.md. These security plugins establish an immutable baseline. They execute underneath the prompt layer, preventing unauthorized modifications to configuration files, regardless of what the LLM is instructed to do. Without this hard-coded layer, an agent instructed to read a local text file will indiscriminately output everything it finds, exposing plain-text GitHub credentials directly to the user interface. But look at the output from a plugin-hardened agent. The runtime layer intercepts the credential extraction mid-process, replacing the raw password with a padlocked policy notice while preserving the legitimate portion of the request. The limitation here is adaptability. Plugins execute predefined risk patterns. If an adversary uses an attack sequence outside the compiled rule set, the plugin lacks the cognitive capacity to recognize it. Plugins secure the structural baseline, but as the primary agent learns and expands its capabilities, a rigid, static defense mechanism creates a growing vulnerability gap over time. Closing that gap requires moving security entirely outside the agent's internal logic. This brings us to Layer 3, watcher-based protection. This relies on the principle of regulatory separation. The safety logic is detached from the primary task executing agent, splitting the workload into parallel, isolated pathways. As shown in this architecture map, the watcher is a dedicated, structurally independent OpenClaw instance. Its only connection to the primary agent is a persistent WebSocket telemetry stream. Because the watcher operates entirely outside the primary agent's plugin namespace, process isolation is maintained. a user issuing malicious commands to the task agent has no pathway to uninstall the oversight protocols. Externalizing the oversight alleviates the tension between task performance and safety compliance. The primary agent focuses on execution without the overhead of self-policing, while the watcher maintains independent supervision. Deploying a dedicated LLM as the auditor, rather than relying on standard code logic, provides a distinct operational advantage: the ability to understand complex intent. The watcher ingests a continuous live stream of session telemetry. It evaluates the agent's contextual state, the sequence of tool invocations, and the nuances of multi-turn messaging to diagnose behavioral anomalies. If the primary agent attempts a high-risk system modification or falls into an unbounded autonomous loop, the watcher forcibly halts the execution workflow, switching the system state to require explicit human confirmation before proceeding. This new architecture offers high deployment flexibility. Bose agents can run locally to maintain host-level data privacy, or the watcher can be deployed as a centralized cloud service to govern massive, multi-agent enterprise clusters. This architecture establishes the watcher as a context-aware supervisor. It monitors the execution flow in real time, providing an intervention layer that functions independently of the agent's own code. To validate this architecture, ClawKeeper was benchmarked against the OWASP Agentic Security Guidelines and prominent open-source defense repositories. This grid chart illustrates the fragmentation in the industry. Competing frameworks act as isolated point defenses, covering only a fraction of known threat categories, while ClawKeeper fills all 7 columns with success rates between 85 and 90. The empirical result is clear. Unifying skills, plugins, and an independent watcher yields a 15 to 45% improvement in overall defense success compared to the best isolated solutions available. In a high-privileged environment, defense success depends on closing the gaps left by isolated tools. While individual layers block many attacks, the combined architecture is what pushes the success rate toward 90%. The ultimate advantage of the watcher paradigm is security self-evolution. Because the watcher is an autonomous LLM, it continuously updates its own threat models and in-context memory. Every time it encounters a novel adversarial pattern in the wild, it refines its detection parameters. This chart visualizes that trajectory. Over the course of processing 100 complex, previously unseen threat cases, the watcher's defense success rate scales dynamically from an initial 90% up to 95%, without manual code updates. Crucially, this middleware isn't restricted to OpenClaw. The decoupled watcher can be adapted to secure any future agent framework by simply establishing a clean communication interface. As AI moves toward a more autonomous, operating system-like role, static security measures will struggle to keep pace. Decoupled, self-evolving oversight provides the structural framework necessary to manage the risks of these increasingly complex systems.